Hey everyone, Xiao here. Thanks for stopping by. In my last video, I shared my experience running DeepSeek R1 with the Intel Arc B580 GPU using Ollama. But I felt there had to be ways to make it run even faster. So in this video, I documented my experience running DeepSeek R1 with llama.cpp instead of Ollama. On top of that, I overclocked the Intel Arc B580 to push the performance even further. I'll break down the results and explain why I think the level of performance we're seeing is a game changer. And finally, I'll share some of my thoughts on Intel. As usual, all the links I mention in this video are listed in the description section. Please note that I'm not providing any advice or instructions. I'm just documenting what worked for me and what I discovered along the way. Before we begin, please read the disclaimer in the video's description. If you've done that, let's get started. Before we begin, just a quick heads up, it would be best to check out my previous video first, as this one builds on what I covered there. You can find the link to my last video in the description section. As I mentioned in my previous video, this is the test system I used for the tests shown here. This setup can be configured for approximately $1,000. I used a high-end CPU cooler and a premium OpenBench case for this build, though they might not be necessary. Additionally, for new builds, I would consider the latest Intel Arrow Lake S CPUs, and I may discuss this topic in future videos. If you're interested, please subscribe to the channel. Let's get started. While Ollama is very popular and user-friendly, llama.cpp is generally considered more performant. To use llama.cpp with the Intel Arc B580, I once again referred to Intel's GitHub IPEX LLM repository, as this build is specifically designed for Intel products. I opened an Anaconda prompt in admin mode and ran the following command to activate the Python environment. If you're having trouble following along, I recommend checking out my previous video, where I cover the setup process in more detail. Then, I created a llama.cpp directory and navigated into it using the cd command. Then I ran the following command to initialize llama.cpp with IPEX LLM. Before running llama.cpp, set the following environment variables to use GPU acceleration. In my last video, I documented my thought process in selecting the DeepSeek R1 14B model with 4-bit quantization for the Intel Arc B580 GPU. For a fair comparison, I used llama.cpp with the same Ollama model as in the previous video. The largest file in the blobs directory is the DeepSeek R1 14B model with 4-bit quantization. Again, I used the same test prompt as last time. Here is the llama.cpp command to execute the prompt. I used a context size of 2048 tokens, which is the default setting for Ollama. Let's see it in action. Again, as mentioned in my previous video, what I did was purely for my technical experimentation with DeepSeek R1. I did not follow any steps suggested by the language model. After the run finished, as seen in the evil time log, the tokens per second rate was 31.17. Running the same model on llama.cpp gave me an 8% performance improvement, with tokens per second increasing to 31.17 from 28.9, compared to when Ollama was used to run the model. For reference, please check my previous video, where I ran the same model using Ollama. What I lost was the convenience that came with Ollama. However, for me, that's not a critical issue since my main use case for LLMs is via API calls. Now, let's discuss my experience with overclocking. The overclocking process was quite straightforward and was done using Intel graphics software. Let's see it in action. What I did was increase the voltage limit by 50%, increase the power limit by 20%, increase the clock speed by 150 MHz, and increase the memory speed by 1 gigabit per second. After confirming the changes, I reran the prompt. As seen in the external screen capture, with overclocking, the tokens per second increased to 32.46 from 31.17 when running at the base clock, a 4% improvement. The downside of overclocking is that the system can become unstable. I think a better approach would be to purchase factory overclocked versions of the Intel Arc B580, such as the ASRock Steel Legend. This slide is the highlight of the talk. By switching from Ollama to llama.cpp and applying some overclocking to the B580, I was able to increase tokens per second from 28.9 to 32.5, a double-digit increase. While the tokens per second measure may vary depending on the prompt, I believe the percentage gain should remain consistent. To put this into perspective, using 32.5 tokens per second as an example, 32.5 tokens per second translates to approximately 1,462.5 words per minute. 1,462.5 words could be equivalent to 500 lines of code generated in just 1 minute. Furthermore, the system running the DeepSeek R1 model costs only around $1,000. The easy accessibility and cost-effectiveness of such technology is truly transformative. Although large language models can generate a high volume of tokens per minute, that output has limited value if it lacks coherence. With that in mind, let's explore DeepSeek's R1 series of models in more detail. DeepSeek's R1 can be considered a family of reasoning models, similar to OpenAI's O1 and O1 Mini. Reasoning models typically generate coherent responses, making them especially useful for tasks such as coding. DeepSeek's GitHub page lists multiple distilled R1 models derived from various base models, as well as an R1 model based on DeepSeek v3. After compiling them into a single table, with fewer reasoning benchmarks, I sorted the models by their 4-bit quantized size. Quantization is a common technique for reducing the memory footprint of large models, albeit at the expense of some accuracy. While this can degrade output quality, tools like Intel Neural Compressor can help strike a better balance between size and performance. Another key benefit of 4-bit quantization is the potential for hardware acceleration on devices optimized for 4-bit integer operations. For instance, the Intel Arc B580's Xe vector engine support INT4 tops directly at the hardware level. Focusing on the R17B, R18B, R114B, and R132B models, all of which can run on consumer-grade GPUs, we compare them to OpenAI's O1 Mini, currently accessible only via paid subscription, with additional API fees. My simple comparisons indicate that R132B and R114B both perform comparable to O1 Mini, while R114B significantly outperforms R17B, the latter being similar in performance to R18B. For hardware considerations, the Intel Arc B580, with 12 GB of VRAM, comfortably handles the R114B model and provides top performance in the $200 to $300 price range. This makes pairing R114B with the B580 one of the most cost-effective ways to run DeepSeek's R1 models locally. You might ask, why not use the 32B model? R132B demands at least 20 GB of GPU memory, making a 24 GB GPU necessary. Such high VRAM cards can cost several times more than an Intel Arc B580. Moreover, while a 24 GB card can run R132B, its larger parameter count usually results in lower token throughput than smaller models. For agentic workflows or applications where throughput is critical, a smaller model may therefore be preferable. That concludes this quick overview of the R1 models. I came up with this idea after several people asked me how to choose Intel GPUs and CPUs for LLM projects. I'm thinking we could collaborate to create content that helps others build systems specifically designed for working with machine learning and AI applications. If you're interested, feel free to reach out to me via YouTube or Twitter so we can discuss potential approaches. Personally, I believe Intel should promote Arrow Lake S within the ML and AI community. For the Intel Arc B580, factory overclocked versions might be more suitable for such workloads. Anyway, those are just a few of my thoughts. And that's it. Thank you for following along on my journey. I hope you all enjoyed the content. If you have any questions about my experience, feel free to leave them in the comment section. If you found this video helpful, I'd really appreciate it if you could hit the like button and subscribe to the channel. Your support motivates me to keep sharing insights like this. Thanks again for watching. Cheers.